to the reconstruction of super resolution fluorescence microscopy.
Okay, thank you. Hi, good afternoon, everyone. My name is Yu. I'm a PhD student from Costa. Today I'm going to introduce our recent work in super resolution fluorescence microscopy, which combines the advantage of deep learning and Bayesian inference. So as we know, the optical microscope is very important for biological research because it is very affordable and easy to use. However, according to the obvious diffraction limit, the maximum resolution that optical microscope can achieve is roughly half of the light wavelength, which is around 300 nanometers. That is, if the distance between two elements of the structure is smaller than this limit, the optical microscope is unable to distinguish or resolve them. For example, here we show a picture of a part of the microtubule. We use A line to point out the 2 points on the microtubule, which are the 2 cross-sections of A line with the microtubule. We also use B line to point out another 2 points on the microtubule. We can see that the distance between the 2 points pointed out by the A line is large enough, so we can see that clearly there is 2 points that across the microtubule. But for the 2 points that pointed by the B line, because their distance is so small, we can't see it confidently whether they are 1 point or they are 2 points. Which means the structure around the B line is not resolved. And here we show the diffraction limit, the comparison of diffraction limit with the size of the common biological entities. As shown in the figure, if we can break the diffraction limit and further push the limit, we can facilitate the research in the biological research in organelle or even in molecular level greatly. And actually in 2013, the Nobel Prize in Chemistry was awarded to Eric Bezig, Stephen Hall, and William Moner for their pioneer research in the super resolved fluorescence microscopy. So in principle, the super resolution fluorescence microscopy still uses the optical microscope, but the output data is a little bit different from legend optical microscopy, whose output is usually a static single image. But for the fluorescence microscopy, the output is a time series images, that is a movie. We can see from the movie, the fluorescence proteins are like the blinking bulb on the structure, which lighten the structure in return. Although using just one frame from the movie is impossible to reconstruct structure, but using the whole movie information, we can reconstruct structure in high resolution. So now the problem becomes to reconstruct a single high resolution image which is noise free from a set of low resolution time series images which is highly noisy. And the information we have is of course first the low resolution images, but on the other hand, we also have the physical process behind this problem very clearly. Notice that this problem is very different from the single image super resolution problem in computer vision field, for which they only know the low resolution image. So what they do is actually trying to reconstruct the super resolution image only using the low resolution image and the distribution done by the deep learning model from the training data. They actually don't know the physical process of downsampling. But on the other hand, since we have the low resolution images and we also have the physical process behind this problem, so is this problem a well-defined Bayesian problem? And actually the answer is yes. Several methods have been proposed to solve this problem using Bayesian method alone. But only using Bayesian method could be very slow. For example, the previous state-of-the-art method, the 3B method, it will take 75 hours to just reconstruct a middle-sized structure. And besides, the Bayesian method may have very high risk of getting stuck in local minima. So why not use deep learning? If we can train a working deep learning on this problem, probably we can reconstruct the structure using just one run of forward propagation, which can take less than 1 minute. But there are some problems of applying deep learning method into this field. The first problem is the data. So we don't have enough low resolution data. And even worse, even if we can collect enough low resolution data by doing a lot of experiments, we are lack of the ground truth. That is, we don't know the actual structure behind those low resolution images. So for trying a deep learning model, we need both the input of the deep learning model and the target that we want to achieve of the deep learning model. So now we only have those low-resolution images. We don't have the ground truth. There's no way that we can train a deep learning model using this real data. And even if we somehow get the low-resolution images and also the target of the deep learning model, the training process is not that straightforward, because previously the deep learning model is always dealing with those noisy-free natural images. But now our image is highly noisy, which means the result of our model may have a lot of fictitious for which we need to deal with. And even if we finally overcome these three obstacles, the method itself may still have some problem. The biggest problem is the deep learning problem itself. We're unable, actually, the deep learning output is lack of physical meaning. That is, we can't explain why we get the result, which is basically current status of almost all the deep learning research. We do not want that kind of result, especially for this problem. We know the physical meaning behind this problem very clearly. But the speed up that deep learning can achieve is so tempting that we really want to apply deep learning method into the field. So to overcome those obstacles, we proposed a new method which combines the advantage of deep learning and Bayesian inference. We call it DLBI. And here is the overview of DLBI. So the big idea is that using the physical process behind this problem, we construct a simulator which can simulate the simulated noisy low-resolution time series image given the high-resolution image. So with this simulator, we can generate as much data as possible, which contains both the low-resolution image and the high-resolution image. That is, we have both the input of the deep learning model and also the target of the model. So with this data, we can train a deep learning model which can reconstruct the super-resolution structure from the input low-resolution images. But we didn't stop here. We want more. We want to further refine the result. And also, we want to make the usage of deep learning method into this problem more reasonable. To achieve that, we further use a Bayesian inference method module, for which they will take the deep learning output as a prior, and also the original low-resolution image as the input, and finally get a result, refine the result. So consequently, our framework contains three modules: the simulation module, the deep learning module, and the Bayesian inference module. So during the training stage, the simulation module would be used to generate those simulated data to train a working deep learning model. And during testing stage, that is, we want to reconstruct the super resolution image from those low resolution images. Both the deep learning module and the Bayesian inference module are used. So those low resolution images would first be input to the deep learning module to get the deep learning output. And then the deep learning output will serve as a prior, together with the low resolution images are fed to the Bayesian inference module to get the final output. So let's break down those three modules in detail. Okay. The first module is the simulation module. So in principle, we use those mathematical models and the experimental calibrated parameters to build up a simulator which can obtain the low resolution images given the high resolution images. So specifically, we use the hidden macro model for the fluorescence protein modeling, and also the fountain point spread function. To make the data more similar to the real data, we also added the DC offset, and then do sampling and added the final Gaussian noise. So with this simulator, we solve the data problem and the ground truth problem. And with this data, we can now train a deep learning model. Next, we need to deal with the fictitious problem. And let's look at the deep learning model in details. So we use generative adversarial network, GAN for short. So instead of training just one network, we will train a pair of networks, the generator network and the discriminant network. So the generator network is a final productive network which can reconstruct the super resolution image from the low resolution images. And the discriminant network is a competitor of generator network, which will distinguish the super resolution image constructed by the generator from the high resolution images, so that to push the generator network to reconstruct the super resolution image as similar to the high resolution images as possible. For the discriminant network, we use the commonly used residual network. But for the generator network, since we need to deal with the fictitious problem, we designed specifically for this problem. And let's look at it in detail. So there are two sources of fake details. Firstly, the data itself is noisy. Secondly, the model itself may also introduce fake details. So to solve the first kind of fake details, we use middle color dropout, design shortcut, and perception loss. To deal with the second kind of fake detail that is introduced by the model itself, we use the multi-scale assembly training process. Due to the limited time, we don't have time to discuss them in detail. If you are interested in these techniques, feel free to discuss me offline. So the last module is the Bayesian inference module. So in principle, this module will take the output of the deep learning model and get the final refined output. It will also further deal with the fake details problem, but more importantly, it endures physical meaning to the deep learning output. That is, it serves as prior as the Bayesian inference module. So this Bayesian inference module makes the usage of deep learning into this problem more reasonable. And with those three modules, we apply the deep learning method into this problem successfully. In terms of the running time bottleneck of Bayesian inference, we will discuss several slides later. But before that, we would like to first show the reconstruction quality. Let's first check the similarity data. So the first row is ground truth. The second row is the low resolution image, one frame. And the third row is the previous data of the art method, the 3B method reconstruction result. And the last row is our result. We can see that compared to the previous state of art result, our result is closer to the ground truth. Specifically, the lines is more natural, continuous, and with much less fake details. We also evaluate it quantitatively. We use the peak signal to noise ratio and the structure similarity ratio, which are the two commonly used criteria in this field. We can see that our method can beat the 3B method consistently across different data sets and across different criteria. And here we also show the performance on the real data. It is similar to the simulated data. And now it's time to check the speed. So this histogram shows the running time comparison of different methods. The running time of the 3B method is shown in yellow bar. The running time of the whole stage of the whole testing stage of DLBI is shown in green bar, and the running time of the deep learning model itself is shown in blue bar. Notice that the y-axis is in log scale. So compared to the 3B method, if we only run the deep learning model, it will bring about 1,500 times speed up. Notice that the output of the deep learning model is good enough. So if you can consider more about the speed and can compromise the mathematical rigors, you can use the deep learning output. And even if we run the whole DLBI testing stage, which contains both the Bayesian inference and the deep learning module, we can still have 150 times speed up. The reason that even if we contain the Bayesian inference module into our stage, testing stage, is that the output of the deep learning model is serves as a very good prior, which enable us to use more aggressive search strategy when doing the Bayesian inference. And also, the good prior makes the algorithm converge faster. So with such a huge speed up, we can do some very interesting things such as the larger field reconstruction and the real-time reconstruction if we set the system properly. And here we show the performance of the larger field reconstruction. So the reconstructed image is very large. It's basically 2K times 3.2K. Since the 3B method is very slow, we are unable to get a result on this such larger data. So we compared our method with the Palmer method. We can see that our method can achieve similar comparable performance as the Palmer method with much less frames, which means using our method, it can cause much less damage to the experimental specimen. Our framework can also be applied to can also have other applications, such as the deep learning output can serve as a very quick prior for the other Bayesian-based method of this field. And our framework can also be applied to other fields, such as medical image processing. Because the physical process of medical processing is already known, we can as we do for the fluorescence microscopy, we can do it similarly to the medical image processing to do the super resolution and further facilitate the image processing. And finally, I'd like to thank all my collaborators, especially these 3 collaborators, Dr. Ming Han from our group, Dr. Fan Xu from ICT, and my supervisor, Professor Xing Gao. The whole program is available on the GitHub, and if you're interested in the other researchers in our group, feel free to look at them on our group page. And thank you very much for your attention. I'll be very happy to take any questions you have.
We have time for some questions. Maybe I just start. I mean, in the specific instance, you effectively used a simulation process of the physical process to train the deep learning approach essentially as a function memorizer. Do you see other ways to incorporate this prior information? Because in a way it's a complex procedure you're running here to incorporate that physical process.
Actually, we are also thinking about why deep learning works. So we think probably deep learning can do the reverse of that process. But it's just a guess. We have no idea why it works.
Yeah. Well, maybe I'll ask one more quick question. Can you comment on the relationship between what you're actively doing in method like approximate Bayesian computations? Because ABC, in a way, uses a similar idea that you simulate from the process and you're comparing the outputting data. I mean, there's some similarities to the GANs that you are showing here and what ABC does. Have you thought about that, or is that?
So, sorry, ABC?
Approximate Bayesian computation?
Ah, that one. I think it might works. We can try. Yeah. Okay. Very good question.
Yeah. Okay, there are no more questions. Let's thank the speaker again.
Okay, thank you.